Hello everyone, welcome to another Applied Circuits video. This one all about the low-pass filter. So a low-pass filter consists of a resistor and a capacitor in series in which we sample our output across the capacitor. The low-pass filter is very simple and very common, found almost everywhere you need to filter out low-frequency signals from your inputs. So the most important property that comes out of the circuit is that the output signal strength scales with the input frequency. How does it work? The capacitor has a reactance that is inversely proportional to frequency, meaning that lower frequencies result in high impedance, which gives a higher voltage across the capacitor when measured. The inverse is also true. High frequencies result in low voltages across the capacitor. So if we are taking our output signal to be the voltage across the capacitor, if we're measuring across the capacitor, low frequencies result in a higher output, which means that low frequencies have an easier time passing through this circuit. Hence, low-pass filter. One factor that many filters state is the cutoff frequency, which is given by 1 over 2 pi r times c, which is the frequency at which half of the power supplied by the input is lost to the circuit and our output is only half of what we put in. Hence, half power frequency. Same thing as cutoff frequency, it's interchangeable. So first, some analysis. In order to determine the response of the filter to variable frequency input, we should determine the functions that give voltage across the capacitor, since that is where we are measuring. We know that the impedance is a function of the frequency already, which in turn informs the current function, which we know from our example problems we did in the last video. And we also know from the example inductor circuit that it is much simpler to use Kirchhoff's law than to try to directly find the voltage across the inductor. Hence, voltage across capacitor is equal to the Cartesian distance between the applied voltage and the resistor voltage. So now that we have our equations and we know basically how to set them up, let's see the response of our filter. Let's assume we're getting an input signal of magnitude 1.414 volts, but whose frequency is changing over time. And let's build our filter with the 1 kilo ohm resistor and a 1 microfarad capacitor. Using our previously found equations, we can plot the response of our filter to the input frequencies. Our cutoff frequency, or half power frequency, should theoretically be at 1 k rads per second. And it looks like the plot that we developed using our equations supports that. And we can see that it is the half power as well, because remember, voltage squared is equal to the wattage or power. So we need to have a factor of 1/2 in front of our power when we square the voltage. And it looks like 0.707 squared is 1/2. And it was this circuit input was designed specifically so that we could see that is 0.707, because if you take 1.414 volts in alternating current, the RMS voltage just is 1, because remember, it's the peak voltage over the square root of 2, so 1.414 over root 2 is 1. And then, now that we have our input, we get our half power frequency, once again, a factor of root 2, 0.707. Nice. And now for a neat application. So let's say we're working for a mining concern, and we want to know where some ore or some oil is. Instead of guessing or walking around poking the ground, we can use a gravimeter. The idea behind that is that metals and oil will have a different density than the surrounding soil, and this different density will create small but detectable differences in the local gravity, which we detect using the gravimeter. So there are two main parts of the gravimeter. The first is the detection part, and one way of making the detection part is by constructing a capacitor with a mass hanging off of one plate. Gravity will pull on the mass as we move it around and deform the plate that it's attached to, and this deformation will cause the distance between the two plates change, and then that change in the distance affects the capacitance. So if we're holding a constant voltage or a constant current across, this change in capacitance will result in a change in voltage or current, which we can then detect. So far so good. But we also need to cover a lot of ground. So what we do we can put it into an airplane. So now we're flying over lots of ground and getting all kinds of readings. But from air resistance and turbulence and just moving around and everything, there are all kinds of vibrations happening, and that's going to also deflect the mass. So we think for a little bit, and we realize that changes in gravity from ore pockets that we're looking for are going to result in slower changes over time than the vibrations resulting from turbulence. Because logically, the turbulence would give rapid bounces because it's basically vibrations of the airframe. So if we pass our input signal through a low pass filter, the really high frequency vibrations resulting from the turbulence get taken away from our signal. And the slower signals generated by the changes in gravity continue through our circuit. Now our data is nice and cleaned up. Great, we've used the low pass filter to help a mining company. Of course, there's a lot more that go into gravimeters and especially into this application of them. But we covered the basics. The next step after this would be to take the Fourier transform to see the different frequencies that are contributing to the signal. And then the different frequencies would tell us the size of locations and the amplitude, the difference in gravitational pull, et cetera, et cetera. But that's for another time. All right, thank you for watching.